In this lesson, we will discuss the fire detection systems fitted to all aircraft. A fire cannot exist without three things being present. These are heat, or a source of ignition, fuel, material that will burn, and oxygen. This is known as the triangle of fire. Take any one of the three away and the fire will go out. A fire in an aircraft is extremely dangerous. So to protect the aircraft, the crew and the passengers, aircraft must have fire detection and extinguishing systems fitted in all areas where a potential fire risk may exist, following failure of or leakage from any component or associated equipment. The specific areas that require protection are the engines, the auxiliary power unit or APU, the main wheel wells, and the cargo compartments. These areas are known as designated fire zones, and they must have detection systems fitted to warn the crew of a fire. In the case of the engines and the auxiliary power unit, they are isolated by fireproof bulkheads, known as firewalls, normally manufactured from titanium or stainless steel, which will contain any fire to the immediate area and prevent it from spreading to the rest of the aircraft. Each designated fire zone must have a fire detection system which is capable of providing rapid detection and warning of a localized fire or overheat condition. There are a number of detection systems in use, and we will now take a look at them. Differential expansion detectors use the fact that when heat is applied to different materials, they will expand at different rates. A detector consists of a pair of contacts mounted on a spring bow assembly, fitted within an expansion tube, which is mounted on a base. The spring bow is fixed to the tube at the top and the bottom. When heat is applied, the tube expands at a greater rate than the bow, drawing the contacts together. When the contacts come together, they provide power to the warning circuit. A subsequent drop in temperature will cause the tube to shorten, the contact to open, and the warning to stop. This type of detector usually incorporates a short time delay before the warning is activated, to prevent false warnings due to vibration. Differential expansion detectors are often used to monitor engine cooling air outlets in order to provide internal engine overheat warning. In the event of this warning being given, the pilots will normally be required to shut down the engine. Engine and auxiliary power unit fire zones are often fitted with continuous loop fire detectors, commonly known as fire-wire systems. A detector unit consists of a stainless steel tube with a central electrode insulated from the tube by a core of temperature-sensitive material. Firewire detectors operate on the principle of their core material having either a negative coefficient of resistance with temperature or a positive coefficient of capacitance with temperature. In one system, both methods are used together. In the resistive type of firewire, as the temperature increases, the resistance of the insulating material decreases. This causes the current flow between the central electrode and the outer tube to increase, until, at a predetermined temperature, sufficient current will flow and the warning system will operate. If the temperature drops back below a preset value, the system will automatically reset, and the warning will stop. This type of detector will react and give a fire warning if there is an isolated temperature increase, for instance, from a direct flame, or if the temperature of the entire detector increases, possibly because of a hot gas leak. Because the loop is connected to the control unit at both ends, the system will continue functioning with a single break in the firewire. One particular problem with this type of system is that a short circuit between the case and the inner electrode will give a false fire warning. In the capacitive type of system, the detector acts as a long capacitor, with the core material acting as the dielectric, and the case and the inner electrode as the poles. The case and the inner electrode are connected across an AC supply. An increase in temperature causes a change in the properties of the inner core material. This change increases the capacitance of the detector. The firewire is polarized by the application of half-wave rectified alternating current from a control unit, which it stores and then discharges as a feedback current. As the capacitance increases with temperature increase, so will the feedback current. Once the feedback current reaches a predetermined level, it activates the fire warning. As with the resistive type, this system will reset itself once the temperature drops below a preset level. This type of detector will also react and give a fire warning if there is an isolated temperature increase, for instance from a direct flame, or if the temperature of the entire detector increases. Again, as with the resistive system, the loop is connected to the control unit at both ends, so the system will continue to operate normally in the event of a single break in the firewire. This system has the advantage over the resistive type in that a short-circuit grounding of the element or system will cause the capacitance to fall to zero, so will not result in a false warning. Firewires are positioned around engine fire zones in a continuous double loop. The two loops are normally known as Loop A and Loop B. The two loops operate independently. Both loops need to detect a fire to initiate the warning. In this way, spurious warnings caused by one loop giving a false fire indication, possibly due to a short circuit, are prevented. Warning of any loop failure may be displayed on the fire detection panel or electronic system display unit. The last system we are going to look at is the gas-filled detector system. This system consists of a number of sensing elements which look very similar to firewire, and they are used in a very similar way. The tube has a central core, made up of a material which will give off hydrogen gas when heated to a high temperature. During the manufacturing process, helium gas is forced into the tube under pressure. The tube is then sealed. To aid explanation of the gas-filled detector type of system, we have included a pressure gauge. This gauge is not fitted on aircraft detection systems. The pressure in the tube is monitored by two pressure switches. One is closed at the tube's normal pressure, This is known as the integrity switch. The other, which is open at normal pressure, is known as the alarm switch. As with firewire, the detectors are positioned around the fire zones in a double loop, with both loops again being required to detect a fire before a fire warning is given. When the gas-filled detector tube is heated locally by a flame, the helium pressure may not increase sufficiently to trigger the warning. However, hydrogen gas is released from the core material, and the pressure in the tube will build up. This increase of pressure is sensed by the alarm pressure switch, which will close. This will send a signal to a control box, which will initiate a fire warning. In the event of a hot gas leak, the temperature increase will be less than that caused by a flame, but it will be felt over a larger area of the detector. This increase in temperature may be insufficient to cause the release of hydrogen gas, but it will cause sufficient increase in the pressure of the helium gas to close the alarm pressure switch and initiate a fire warning. Should the tube be damaged and the helium gas be released from the core, the pressure will fall, and the normally closed integrity pressure switch will open. This will cause a fault indication on the control panel or electronic systems display. Whichever detection system is used, flight deck indications of an engine fire will normally be both oral and visual. The oral warning will normally be a bell or a klaxon, or possibly a continuous repetitive chime. Visually, there may be a master fire warning caption and a steady red fire warning light for each engine. Before flight, a means must be available to test the fire warning circuit. A fire test selector is therefore provided for the flight crew. With differential expansion detectors, a simple continuity test is carried out on the wiring between the detector or detectors and the warning light. A satisfactory test is indicated by illumination of the warning light. When a fire test is initiated on a firewire system, a continuity test is carried out on both the outer tube and the inner electrode. A satisfactory test is indicated by a full fire warning being displayed for all engines being tested. Should there be a break in either the tube or the electrode of the firewire for a particular engine, then the test will fail, and a fire warning will not be given for that engine. When a fire test is carried out on the gas-filled system, again the integrity of the loops is tested. But also, if the gas has leaked out and the integrity switch is open, then the test will fail. In some firewire and gas-filled detector systems, a warning is given to notify crews if a single fire loop should fail in flight. The system may now automatically switch to single loop operation, with a fire warning being given if the serviceable loop alone senses a fire. Depending on aircraft type, a limited number of sectors may be permitted to be flown in the single loop mode. That is the end of the lesson. Here is a summary of the main points. Click to go on to the next one once you are sure you understand the point being displayed. The areas of an aircraft fitted with fire protection systems are the engines, the auxiliary power unit, the main wheel bays, and the cargo compartments. Differential expansion fire detectors use the fact that when heat is applied to different materials, they will expand at different rates. Remember that these detectors usually have a time delay built into their warning circuits to prevent false alarms caused by vibration. Resistance and capacitive firewire systems have the detector connected at both ends. So with a single break, the detector will continue to function. The system test checks the continuity of the loop as well as the warning system, so if there is a break, the test will fail. If a resistive firewire is short-circuited, it will give a fire warning. The gas-filled system uses the fact that the pressure of the gas in the detector increases with increasing temperature to trigger a fire warning. When a test is carried out on the gas-filled system, the integrity of the loops is tested. If the gas has leaked out, the integrity switch will open and the test will fail. Finally, flight deck indications of an engine fire will normally be both aural and visual.